Welcome back to Momentum 99. In this video, I'll be showing you people how to draw the space diagram for the given slider crank mechanism. To begin with, the given data is we have given in the problem the crank length is AB is equal to 100 mm. Moving on to the position of the crank, they have given the crank angle as theta is equal to 60 degree from the inner dead center. And the last data given here is the length of the connecting rod BC is equal to 300 mm. So in order to start with this space diagram, we need to specify or we need to take a suitable scale here. Now I have taken a reduced scale and the scale I have taken is 1:5. To begin with, mark a horizontal reference line here. Take your protractor, take your any linear scale, just draw a thin line, horizontal reference line, a very thin one, and mark any arbitrary point on this horizontal reference line what you have taken. I'll be just marking a point here. Now next step, with the help of your protractor, since the given angle of the crank is given as theta is equal to 60 degree, I'll be taking this arbitrary point here. With the help of my protractor, I'll be marking 60 degree here from the anti-clockwise direction. Now connect this point, again connect these 2 points with the help of a thin line so that we will be able to draw the dimension, the line with respect to the dimension. Just draw a thin line now. Now the next is they have given the length of the crank or the crank length is equal to AB is equal to 100 mm. Since we are using a reduced scale, we need to reduce this 100 mm to 1:5 scale. In order to do that, what you do is divide this 100, whatever the dimension they have given, divide by 1/5, or multiply the 100 into 1/5 so that you will be getting the answer equal to 20. So this 100 mm length you will be measuring on this particular line segment as 20 mm. Now to mark this one, I will be making use of the compass here. With the help of measuring 20 mm, I will be measuring 20 mm here. Now with this point as the reference, I'll be marking this length here. So I'll be naming these 2 points here. I'll be marking this as A and this point as, I'll be taking this as point B. So now this angle is nothing but we have marked this at theta is equal to, this is 60 degree here. Okay, now they have given the connecting rod length, this is equal to 300 mm. Now again 300 by 5 or 300 multiplied by 1/5, you will be getting the length equal to 60 mm or 6 centimeter. Now again with the help of your compass, measure 60 mm, take any scale, linear scale, measure 60 mm or 6 centimeter. Now with this point B as the center, cut the arc on this horizontal reference line what you have marked in the beginning of the video. Now with the help of again the linear scale, connect this point to the point B. So this gives our configuration of the slider crank mechanism. Now name this point as point C. Since we need to draw the slider here, put a square or a rectangle and let's start naming these links from the left hand now. Now I will be having a fixed link here. I will be marking this as link 1, and also the slider moves on the fixed link here. I will be naming this link as also 1 here. Now next to the fixed link we have the crank here. I will be naming this as 2. Crank is connected to the connecting rod. We have this as link 3 here. Now generally links are represented within the circles, and we have the slider here, slider represented by the number 4 here. So let's name these things. 1 is the fixed link, 2 is the crank, 3 is the connecting rod, and 4 is our piston or the slider. Now this is nothing but our space diagram drawn, taking the scale as 1:5. Now this is our space diagram drawn taking the scale is equal to 1:5 now. Now the second step is to draw the free body diagram of all the elements which are in the given slider crank mechanism. Now we need to draw the free body diagrams of the link to the crank, and the link 3, that is nothing but the connecting rod, and the link 4, which is the piston here. Now to begin with, we'll be starting to draw the crank, the free body diagram of the crank here. To draw the free body diagram of the crank, which is at an angle of 60 degree from IDC, you can make use of two set squares here. One is this thing, we have 90, 45, 45 set square, and the other is the second one is we have the 90 degree, and this is 60 and this is 30 degree, and for you people. Now to draw the parallel line, we should first align our set square with respect to this crank, whatever the inclination of the crank here. Now after aligning, now see this edge here, now this is the edge we need to reproduce again. We need to draw a line such that any line drawn, this line should be reproduced parallelly with respect to the position of the AB here. Now what I do is, I will be aligning my edge of the scale with respect to this edge AB here, that is nothing, the crank here. Now next what I do is, I need to draw lines parallelly to this one. So what I do is, I will be aligning the scale here, and to the left edge I will be butting another scale like this thing. Okay, if you want you can take the screenshot like this one. Now next what I do is, I will be moving this set square in the downward direction. Now when I move downward, if I draw a line here, this line will be obviously parallel to the length of the crank here. So what I do is, now this length we have calculated by taking the scale as 1:5. We have drawn this length, the given length was 100 mm. We have reduced the scale to 1:5 so that we drawn that length to be 20 mm. I will be drawing a line segment of 20 mm here. I will be just reproducing the same thing here. Okay. Now this is my line here. Now what I do, this is now drawing the free body diagram. I will be naming these two things here. I will be naming this end as A and this end as B here. Now this is my link 2. Now on this link 2, I need to represent the line of action of the forces, that is nothing but F32 and F12. F32 is nothing but the force which is being transformed from, or which is being transmitted from the link 3 to link 2, and F12 is nothing but the force which is being transformed or transmitted from the link 1 to link 2. In order to represent these forces, again I will be making use of the set squares here. First I will be aligning my set square to this third link line segment here on the space diagram. Now what I want is, I need to draw a line that should come parallelly like this thing. So where I should butt the set square here now. Now next what I do here, I will be taking another scale here, and I will be butting the scale here at this end. Getting this thing? Now if I move the scale in the downward direction, I will be butting there's two scales like this. Now this edge is parallel to this connecting rod here. Now I will be moving this line in the downward direction till I get the edge of the length B here. Now slide this thing downward. You'll see that you will not be missing the alignment. If you have missed the alignment, just again rearrange this thing. Now move this scale in the downward direction till you meet the edge B. Okay. Now after getting this thing, draw S from the point B, so that you will be getting the direction of the force F23. Now again I also need another line of action F12. F12 is parallel with respect to this thing. Just draw the line here to show this thing. Okay. Now this line, both the lines should be parallel here. Now after drawing this one, indicate this direction. This is nothing but, this will be the link 3 and this will be the link 1 here, fixed link. So this force transmitted here is F32 and the force transmitted in this direction is F12. Getting this thing? This end is nothing but end A, this is end B, and this is the free body diagram of my link. The first link, that is nothing but, the second link, the crank here. Moving on, next is I need to draw the free body diagram of the third link here, that is nothing but the connecting rod. Now to draw the free body diagram of the connecting rod, again what I should do, I will be reproducing this line segment BC again very next to this one. To draw a line parallel to the connecting rod, what I do is, first I will be aligning my set square along this line segment BC here. Okay, now I'll be aligning this edge with respect to the edge BC here. Next, what I want to do, I want to get a line which will be parallel to this line segment. Now I want to move it in the downward direction. So what I need to do is, first I will be aligning the set square along the line segment BC on the space diagram. Now if I want to move this in the downward direction, I will be butting this small scale on the left side direction, and I will be moving this in the downward direction here. Now butt this properly and move this in the downward direction. If you want to move it towards your right, you can keep the scale like this, and you can move in the opposite direction. So when you think this is the proper position to draw the parallel line with respect to your connecting rod, let's just draw the free body diagram of your connecting rod here. Now what was the line segment we had drawn here? The line segment was, the given length was 300 divided by 5. So our line segment was 6 centimeter. So I will be taking 6 centimeter length here. Now 5 to 11. Now and I will be just extending this line by a bit 1 centimeter in order to represent the line of action direction of the forces. Now what I do here next is, I will be representing this one. Now what is this one? This is nothing but my end B, and this is my end C. Now after drawing this thing, I need to indicate the forces which are acting on the given link, that is nothing but the connecting rod 3. In order to represent the link, I will be representing the number within the circles. So the directions here are nothing but, we will be indicating the forces which are acting on the third link. Now from this space diagram, the crank will be exerting certain force on the connecting rod here, so that I will be in this particular direction. The force acting here is nothing but F23. And since the connecting rod is connected to the piston here, the piston will be exerting the force on the connecting rod, that is nothing but F43. This is how the free body diagram of the connecting rod is done now. Moving on, the last free body diagram to be drawn is that of the piston or the slider here. So I am representing a small rectangle in order to represent the given slider. Any dimension, there is no fixed dimensions here. You need to represent any square by a square or a rectangle, the given slider. Just close these ends and mark the center point. Now what I need to do is, we know that from the diagram here, the force acting, we have an external force here. This is nothing but P is equal to 1 kilonewton, right? Now I need to represent this force here. There is nothing but all the forces acting on our piston here. Now to represent these forces, we will be drawing the free body diagram of the piston here. Now I need to draw a line which is parallel to the piston force here. Now I will be aligning, this is the line of action of the external force here, if you are able to see this one. Now this line is nothing but P is equal to 1 kilonewton. I will be aligning my set square or any linear scale like this one, and I need to have a line parallel to this one. So in order to push this set square in the down direction, I will be butting my another set square in the left direction, and I will be pushing this towards the downward direction. Okay. And if you want to move this towards the left side, again butt this towards the upper direction, upper face, and move your scale towards the left side. Again what you want to do, you want to move this in the downward direction. You can make use of all the scales you have. You can butt in this face, butt near this face, and push your scale in the downward direction. When you feel this is the center point, just draw the parallel line. Now this line, what it does, it is indicating our force, external force P is equal to 1 kilonewton or 1000 newtons. Okay. Now the second force which is acting on our piston is from the connecting rod. There is nothing but from 3 to 4. We have an instrument called as here the roller circle. This is what it looks like. Now this is used to draw parallel lines. So how you will be drawing like this one? See, now we need to indicate this line. There is nothing but from 3 to 4. The force transmitted from 3 to 4. We have already drawn this line of action here. So if you want to draw a line parallel to this one, just align this one, and you can move this roller in whichever direction you want. So I will be making this one move till this here so that it meets this point, and we just draw a thin line here in order to indicate. So this is what? This is nothing but this indicates the line of action F3, 4. This is my fourth link. There is nothing but the piston and the slider. This is my F3, 4. And the last line to be indicated is, there is nothing but the perpendicular force which is being acted upon from the ground to the towards the piston here. Now this is my 90-degree line that I should be drawing here. Now in order to represent the force, the frictional force between the link 1 and link 4, make use of your protractor here. Align this with reference to the horizontal axis here. Mark a point here at 90 degrees, since it will be acting at right angles. Draw a very thin line in order to connect these 2 points here. A very thin line. Now we need to draw a line which is parallel to this particular line here. We have drawn this line here, a thin reference line here, and we need to move this scale towards our left direction. Take any scale, linear scale you have. Align this or butt it in the down direction here. Butt it like this here, and move your scale towards your left hand till it reaches the required point here. Now after it touches the required point, draw a line here. So this line indicates our force transmitted from the first link towards the fourth link here. Now see here, from the free body diagram we have got the direction of F32 and F12 of the crank here, and also from the connecting rod free body diagram we have identified the direction of force F23 and the force F43, and from the free body diagram of the slider we have got the directions of this F34 and F14. The next step, that is step 3, is to draw the force polygon of all the links here. Force polygon of all the links. To start with, we will be drawing the force polygon of the slider here. Since there are 3 forces and these 3 forces are concurrent forces, we will be starting to draw first we will be drawing the force polygon of our link 4 here. Let's start this one. Now in order to draw the force polygon, I will be taking a suitable scale here. Now the scale chosen here is we need to represent this P is equal to 1000 kilonewton in terms of a linear scale here. So what I do is, I will be taking, let 1 centimeter, this is equal to 200 newtons. So how many centimeters I need? 1000 divided by 200, I will be getting the line segment as 5 centimeter. Now I will be taking a scale here. What I do is, from the given free body diagram, I should be drawing the force polygon. Now in order to draw the force polygon, what I do is, I will be aligning my set square or scale with reference to this applied load here. So next is, I will be drawing a parallel line. I will be moving this in the downward direction, or else you can make use of this roller circle if you have. Align this one, drag it in the downward directions, and now 1 centimeter is equal to 200 mm. We need to represent 1000 mm. So we need 5 centimeters. So I think this line. Okay. Now from this free body diagram, our force P is equal to 1 kilonewton is moving towards the left direction. So this direction is also should move in the left direction here. Okay. Now I will be taking this point as O and this point as A here. Now next is, I need to represent this F34 on this force polygon of the slider. I will be taking this roller and I will be dragging it in the downward direction till it touches the starting point of my line segment OA. Now when it touches this one, now see here, only I know the direction, I do not have any magnitude of like this one. Here we know the direction is P is moving in the leftward direction and the magnitude was 1000. But F34, we know only the direction, we don't know the magnitude here. Getting this thing? So what I do is, we do not know to what extent the line segment needs to be drawn. So what I do is, I will be drawing a very thin line here. Okay. From the starting point as A, I will be drawing a line segment. This line segment should be parallel to the line of action F34. Clear? Now next is, I will be taking this point O as the reference here. Now see, we have drawn this P, that is nothing but magnitude and direction represented by OA, and F34 is starting from point A. I have drawn a line, inclined line, which is parallel to F34, and this should move towards the center. And last is, I need to represent this force F14 here. We know the direction, aligning this Parallelly, I'll be moving this one until it touches my line segment, the starting point O here. After it touches the point O, I'll be drawing a line such that it crosses the previous drawn line here. Now I'll be marking this intersection point as B here, and this is my force F14. Now if you look at this arrow marks, from O to A, my force is traveling towards left, and F34 is traveling towards the downward direction. Hence I have represented the arrow mark in the downward direction, and F14 is acting vertically upwards from the free body diagram. Hence I will be representing this F14 in the vertical upward direction. Now whenever you draw a force polygon, it should be of a cyclic order, and it should obtain a closed diagram like this one. Close is nothing but we have closed this one. Now if this is 5 centimeter, according to this one, if we measure the length of AB and multiply it by this one, we will be able to find out our force F34. So in order to get the value of F34, I will be measuring the length AB and multiplied by whatever the scale I have used, I will be getting the value of F34. Similarly, measuring, in order to get the value of F14, I will be measuring the length OB. That is nothing but both AB and OB are measured from this force polygon, multiplied by scale. I will be getting the value of the force F34 and 14 here. Now let's calculate this forces F34 and F14 with the help of any linear scale. Measure this length AB from this force polygon. This will be 5.3 centimeters here. Multiplied by this, as this formula says, scale. Scale have taken to be 200. Now 5.3 into 200, you will be getting the value as 1060 Newton here. Now also I need to find out the second force here, F14. I need to calculate, I need to measure the length OB here. Now measuring this length OB, this is 1.8. The length is, I have measured the length OB to be 1.8 centimeter. Keep this length in centimeter, multiplied by 200. Let's see what we will be getting the answer as. 1.8 multiplied by 200, you will be getting the answer as 360 Newton. Next is I will be drawing the force diagram of the crank as well as on the connecting rod here. Now to draw the force diagram of the connecting rod, what we need to do is, again we have to reproduce this same diagram or the same length or same configuration of the connecting rod here. I will be moving this sheet so that we will be having better view here. Now I will be drawing this length. I need to reproduce this thing. So what I do is I will be aligning this. I will be moving this towards the right side now. I will be moving it, and I need to move it further downwards so that I will be having the much space to draw the diagram here. So this is this thing, and the length is the length of the connecting rod was found out to be 300 by 5, 6 centimeter. So starting from 6 up to 12. So this is the force diagram of my connecting rod here. Now on this line segment, I will be marking this point as whatever the nomenclature used in the this space diagram. This is B and this is C, and this is my 3 connecting rod. Now I need to represent all the forces which is acting towards the link 3 from the different elements, and also the forces which are acting away from the link 3 here. So this is the force diagram of the link 3 here, and the forces which are acting from the link 3, which is moving from the link 3 towards the other direction, other links, I will be representing here, and I will be putting an arrow. So from the link 3, the force which is moving towards in this direction is nothing but from the 3, the force will be transferred to 2, hence I will be writing it as F32. And also if you look at this diagram, from whatever the force from the piston, it is moving towards the third link here, hence whatever the direction of forces which is towards or in the upper direction of 3, and I will be representing this force F43 here as well. So any forces which is moving towards this 3, now 4 we have F43 which is moving towards 3, and F32 which is moving towards from 3 to 2, hence I will be representing these two forces also. Now also if you consider this diagram, F21 which is also moves from this particular force F21, which moves from the link 2 to link 1, hence I will be representing this F21 here. Now, since this is a body which is acted upon by this kind of forces, there will be reaction forces which will be acting in the opposite direction, and these forces are represented by an arrow which is directed away from the link 3 here. Now, in this case, the link 3 will be exerting certain force on the piston here. Now, this force is nothing but equal and opposite to F43. I will be representing this as F34. And F32 is nothing but force which is being exerted from 3 to 2, and there will be certain force which will be exerted from 2 to 3. That equivalent reaction force is given by F23, and I will be represented in this direction now, moving towards the right. And last is F21. The symmetric and opposite to this force is F12. This is how the different forces are represented here. Now, taking the symmetricity, we know that whenever a body is acted upon by two equal and opposite forces, these two magnitudes should be equal and they should be in opposite direction. So, what we do while drawing the force polygon of our link 3, we will be making the symmetricity equations here. Now, the symmetricity equation goes like this. F43, this is equal to F34. These two upper one, and next we will be taking this is equal to F32, this is equal to F23. Now this is equal to remaining two forces F21, this is equal to F12. Now in the previous step we have found the answer of F34, this is equal to 1060 Newton. So all these forces will be having an equal magnitude of 1060 Newton, and the directions are different. Now we need to draw the force diagram of our second link, that is the crank. Again we need to reproduce this free body diagram what we have drawn here. That is nothing but to the same scale, 1:5, same as our space diagram here. Now align this roller scale with respect to the length whatever the free body diagram of your crank you have drawn here. Now slide this in this direction. Mark this one. Now what was this thing here? We had crank length of 100 by 5. This is nothing but 2 centimeters. Now from this free body diagram it is evident that we have a force F32 acting on the second crank here. We need to draw a line. Now this is my point B and this is my point A. Now through point B, I need to represent the line of action of F32 here. Now since we have already drawn the line of action F32 here, I will be aligning my scale here, and I need to move it vertically downward, so that with the help of this bigger set square, I will be butting here and I will be moving it in a downward direction. Now it is crossing my point, so I need to move it in a downward direction here. Again manipulate this thing, butt it in this side and move it further down so that it will be touching the point here. Now after crossing this point, just draw a thin reference line here. Now again what you need to do, you need to draw the line which is passing to the point B, again with reference to this particular line. Now what you will be drawing, this is nothing but, from this diagram it is evident that this is nothing but the force F32, right? Now I need to indicate this force F12, so that what I will be doing, taking this as the reference line, inclined line, align your roller scale here. Now push it towards the downward direction until it touches the point A, and draw a line parallel to the line of action F32. Now this is nothing but our F12, the force which is being transmitted from 1 to 2 here. Now next we need to find this lateral distance, the distance of separation of F12 and this line of action F32. Mark any point on this thing. Take your protractor, align with respect to this arbitrary point what you have marked here. Select or mark 90 degree. Take the ruler from this point, connect to this point 90 degree with the help of a thin line, and this is our nothing but H. Now the T which is acting here, we need to find the value of the torque T2 acting at the link 2 here. Now to find out this torque T2, we have a formula given by, torque is generally defined as force into perpendicular distance. Now this F12 and F32 both are equal from this the previous section what we have seen here. So I'll be taking any force here. For example, I'll be taking F32 itself and I'll be multiplying it by the distance h here. Now I need to measure the value of h here. Now from the diagram, let's see what is the value of h here. So measuring the length of h from the diagram, it is found out to be 2.1 centimeter. Now this h should be multiplied by whatever the scale you have taken in the space diagram here. Now space diagram, we have reduced the scale to 1:5. Hence I will be multiplying my h value with a factor of 5 here. Now when multiplied by 5, we will be getting this as equal to 10.5 centimeter. Now substituting here, we will be getting torque is nothing but F32. From the above step, we have got the answer to be 1060 Newton. I will be substituting here, multiplied by the h value, that is 10.5. Now multiplying this, I will be getting the value of this torque to be 11,130 Newton centimeter. Now if I want to keep this in metric or in terms of Newton millimeter, I will be dividing this answer by 100, so that I will be getting the value of torque to be 111.30 Newton millimeter. This is the answer. That is nothing but a torque that should be applied at the crank in order to keep our slider crank mechanism at static equilibrium condition. Now in the description, I have uploaded the scanned PDF of this, whatever the calculation part I have done, so that it will be helpful for you people. You can find the link in the description so that you can download this calculations what I have done for this particular static analysis of a slider crank mechanism. Thank you.